Now let's learn about methods of preparation of colloidal solutions. Colloidal solutions can be prepared by chemical methods. Let's first learn chemical methods. Chemical methods. Look at this example. If arsenic trioxide is treated with H2S, if you bubble H2S in a solution of arsenic trioxide, then you get arsenic sulfide sol. The driving force for this reaction is the low KSP of arsenic sulfide when compared to arsenic oxide. Next, if you bubble SO2 gas and H2S gas in aqueous solution, you get sulfur sol. You can realize this is the case of cum-proportionation. Oxidation state of sulfur is +4 in SO2 and -2 in H2S. So this gets oxidized at the expense of this. So it's a case of cum-proportionation. These are atoms of same element in different oxidation states. They arrive at one particular oxidation state, that is 0. So it's a case of cum-proportionation. Look at this case. AuCl3, when it is treated with formaldehyde, AuCl3, Au3 plus, Au has a very high SRP. So Au3 plus has a great tendency to transform into Au. That means it can get reduced and this will get oxidized. So formaldehyde gets oxidized to AuCl3 becomes Au. So this is another case of preparation. You get a gold sol here. This is sulfur sol. This will be arsenic sulfide sol. This is the sol, arsenic sulfide sol. Let's look at another method. Ferric chloride, when it is hydrolyzed, this is a hydrolysis reaction. While this is a redox reaction, this is also a redox reaction. This is a displacement method. Ferric chloride on hydrolysis gives ferric hydroxide. Of course, you get HCl. So this is the substance which forms the sol. Here you get metal hydroxide sol. Here you get metal sol. Here you get sol of sulfur, that is non-metal, and it's a metal sulfide sol. So these are few methods of chemical methods of preparation of colloidal solutions. So remember, colloidal solutions can be prepared by displacement reaction, can be prepared by precipitation reaction, that is reaction, double decomposition reaction, you can say hydrolysis reactions, redox reactions. This type of reactions can give rise to colloidal solutions. Now let's talk about another type of method of preparation of colloidal solutions. Just go through these equations once again. Arsenic trioxide becomes arsenic sulfide. The driving force is the low KSP of arsenic sulfide. Here it's a case of cum-proportionation, same element in different oxidation states, they reach one particular value. And then this is a case of reduction of Au3 plus into Au, formaldehyde gets oxidized to formic acid. This is just a simple case of hydrolysis. Now let's move on to the next method of preparation of colloidal solutions, that is Briggs arc method. Let's see Briggs arc method. This is applicable for preparation of metal sols only, metal sols, and that too you can prepare sols of less active metals. What you need to do is take some alkaline solution, it's a alkaline water, and then put 2 metal rods. You use that metal whose sol you want to prepare. For example, you want to prepare silver sol, use silver rods and connect them to a source of high potential. Then what happens, an electric arc is struck between the 2 rods and the temperature in this region becomes very high and the metal volatilizes and again condenses in the solution. Alkali is added to stabilize the sol. So metal volatilizes and condenses in the liquid and you get the corresponding metal sol. You can use gold sol, you can prepare gold sol, silver sol, and metal sols can be prepared by this method. This is called as arc method. We use a source of high electric potential, that is arc method, Bredik's arc method it is called. So this can be taken as another method of preparation of gold sol. You use gold rods and pass high voltage current. Number 3 in the list is peptization. This is another method of preparation of colloidal solutions, peptization. Peptization means transformation of precipitate into colloidal solution. This involves transformation of precipitate into colloidal solution. This transformation is called as peptization. Precipitate is basically a suspension, whereas you cut down the size of the particles and you get colloidal solution. You know, colloidal solution, colloidal particles have size in between the particles of true solution and the suspension. Now what you need to do is you add a suitable electrolyte. If a precipitate is shaken when in a small quantity of electrolyte along with dispersion medium, then you get a colloidal solution. To give you an example, see, if you have AgCl, add little extra KCl, then you get AgCl sol. What happens is Cl minus will get adsorbed on the particles of AgCl precipitate, and they get scattered due to like charges. They tend to repel each other and they get scattered, and you get the sol. So what we need to do is, this is our precipitate. What we need to do is take the precipitate and add a small amount of electrolyte and see to it that the electrolyte has a common ion. Here the common ion is chloride. Chloride is a common ion. So shake it with an electrolyte having a common ion and you get a colloidal solution. This type of technique is called as peptization. Transformation of precipitate into colloidal solution is called as peptization. We are now going to talk about methods of purification of colloidal solutions. Number 1 in the list is dialysis. Here colloidal solution is taken in a parchment paper bag and it is dipped in a dispersion medium. Then through the pores the electrolytes and the molecules come out and you get pure colloidal solution. Look at this. This is dispersion medium. In this we need to put our colloidal solution in a parchment paper bag, right. This is our colloidal solution. This is a parchment paper bag. Then what happens, the molecules, smaller molecules and the ions of the electrolyte come out through the pores into the dispersion medium. You have dispersion medium here. Outside the bag you have, it is being dipped in dispersion medium. So the particles from inside will come out and what you will be left out here is pure colloidal solution, which is free from smaller particles, that is smaller molecules and even the ions. So this is called dialysis. This is the principle involved in the dialysis done to the patient suffering from kidney failure. Then you have another technique which is quite similar to this, electrodialysis. This is particularly useful if the contaminant, that is if the impurity present in the colloidal solution is electrolyte, then electrodialysis will help. What we just have to do is put two electrodes in this and pass current. Then that will speed up the removal of ions from the colloidal solution. The ions come out due to potential difference and they move towards oppositely charged electrodes, and in this way the solution will be free from ionic species. That is electrodialysis. Then you have another method, ultrafiltration. See, if you use ordinary filter paper, the pore size will allow colloidal particles to pass through it. But here we need to use a special filter paper, that is ultra filter paper. What you need to do is dip ordinary filter paper in a substance called as collodion. Collodion is a substance obtained by nitroglycerin. It is made into a solution by adding a mixture of ethanol and ether. In a mixture of ethanol and ether, we dissolve nitroglycerin, and the ordinary filter paper, this is collodion, right? Ordinary filter paper is dipped in a collodion and it is removed and then hardened by dipping in formaldehyde. So this will decrease the pore size of the filter paper. Such a filter paper is called as ultra filter paper. Now, when you pass colloidal solution through the ultra filter paper, then the particles, smaller particles, ionic species, all those pass through the filter paper. What is left out on the filter paper, the residue, consists of colloidal particles. Put it in fresh dispersion medium and you get purified colloidal solution. That is ultrafiltration. So, for ultrafiltration, we need a special filter paper of smaller pore size. The ordinary filter paper can be transformed into ultrafilter paper by dipping it in collodion and hardening it by dipping it in formaldehyde solution. That's about preparation of colloidal solutions. We are now going to talk about properties of colloidal solutions. Properties of sols. Sol is an abbreviation generally used for colloidal solutions. We are now going to talk about some properties of colloidal solutions. Number one is charge on the colloidal solution. See, colloidal particles develop charge. They generally develop charge. The charge arises due to several reasons. One reason is preferential adsorption of a particular type of ion on the surface of colloidal particles. Another reason is during electrode dispersion, that is arc method, the electrons get adsorbed on the surface of metal particles and you get negatively charged sol when you prepare metal sol with arc method. Let's see how the charge arises in case of electrolyte, precipitate, which is transformed during peptidization. The precipitate is transformed into colloidal solution. Let's see how charge appears on such cases. Look at this case. I have AgNO3 and I am adding Ki. Now I can think of two possibilities here. No doubt I get AgI in both the cases, but then if I use excess of Ki, then the excess I minus will get adsorbed on the surface of colloidal particles. In this way I get negatively charged sol of AgI. But if I take excess of AgNO3, then Ag plus is the common ion and it gets adsorbed on the surface of colloidal particles, and in this way I get a positively charged sol. So during the preparation of colloidal solutions, see, this can be achieved even after precipitation of AgI. You add little Ki to the precipitate of AgI, then it can be transformed into negative sol. If you add AgNO3, you get positive sol. So it all depends upon what substance you have taken in excess. Then the common ion gets adsorbed on the surface of colloidal particles, and that is responsible for development of charge on the colloidal particles. Look at this case. If I add dilute acid, then ferric ion gets adsorbed on the surface, and you get a positively charged sol. The reason is when you add dilute acid, some of the ferric hydroxide will react with it. Its OH minus will be used up in the formation of water. Some ferric ions are produced. Those will get adsorbed on the residual precipitate, and you get positively charged sol particles. If you add alkali, then you get FeOH taken thrice OH minus. You get a negatively charged sol of ferric hydroxide. In alkaline medium it gives negative sol, and in the acidic conditions it gives positively charged sol. Here I have given you a list of examples of positively charged sols and negatively charged sols. Let us look at positively charged sols. Metal hydroxides, like for example ferric hydroxide, such a sol is positively charged sol. The reason is ferric hydroxide is formed due to hydrolysis of some ferrous salt, and ferrous salt solutions are generally acidic. So, because of acidic condition it gives rise to a positively charged sol which consists of ferric getting adsorbed on the precipitate ferric hydroxide. And then basic dyes, because of their basic nature they have an ability to pick up proton and they form positively charged sol. Example of basic dye is methylene blue. Hemoglobin is another very important example of positively charged sol. Now look at the examples of negatively charged sols. Metal sulfides. Metal sulfides are negatively charged sols. Again, by default they are negatively charged because their formation involves alkaline condition, so they are more likely to form negatively charged sol. And then metal sols. Metal sols are generally prepared by arc method. In arc method electrons are involved, an arc is produced and some electrons get adsorbed on the surface of metal particles. And then acidic dyes are also negatively charged sol because they have an ability to lose H, as H plus being acidic, and they form negatively charged sol. Example, Congo red is an acidic dye which is capable of forming negatively charged sol. Starch, gum, gelatin, these are organic substances, they form negatively charged sol. Even clays are silicates, so they form negatively charged sols. So these are some examples, some important examples of colloidal solutions carrying a particular type of charge. This is very important. Generally questions are very often asked from this part. They give a list of 4 different colloidal solutions and ask which of these can be a positively charged sol or which of these can be a negatively charged sol. So you can pick up from the options. Please remember, hemoglobin is a positively charged sol. Hemoglobin is a positively charged sol. Generally the organic substances like starch, gum, gelatin, they form negatively charged colloidal solutions. In this type of inorganic substances, the mode of formation is very important. Whether these are formed under acidic condition or alkaline condition matters. Under acidic conditions, generally substances give rise to positively charged sol due to coordination of H plus on the colloidal particles.